Welcome to Block 1, Using Space. In this lesson, we'll explore space in our lives to understand the compelling reasons we go to the time, trouble, and expense, as well as risk, to venture into space at all, and the basic types of space missions that take advantage of these reasons. So let's get started. We'll start by looking at the course roadmap. The course is divided into 3 blocks. In this first lesson of the Using Space block, we'll examine the topic Space in Our Lives. The primary reference for this lesson comes from Understanding Space, an Introduction to Astronautics, Chapter 1, Section 1. We recommend you read through this section either before or after watching the video lecture. In this lesson, we'll begin by examining the fundamental question of the entire course. Why space? What are the advantages that space offers? We'll then highlight the key missions that leverage those advantages. Our objectives this lesson are for you to be able to list and describe the 5 unique advantages of space, along with the common types of missions that leverage those advantages. So with that background on the lesson complete, let's launch right into it. If you're taking this course, it's because you work directly in the space industry or related field that supports it. Or possibly you just have a personal fascination with the exciting world of astronautics. Regardless of what brought you here, the first question to grapple with is, why space? Clearly, getting into space is dangerous and expensive, and we'll see why in great detail throughout the course. So why bother? Why go to all the time and trouble? Why spend the money to launch robotic missions to orbit to other planets? Or risk the lives of astronauts going to the International Space Station? Why space? As we'll see, space offers a number of compelling advantages that make its exploitation advantageous to the U.S. and other spacefaring nations for their national security and scientific research. It also offers lucrative opportunities to international corporations interested in the bottom line. We'll call these advantages the space imperatives, the overriding reasons that make space missions useful and inevitable. We'll look at 5 of them. The first and most important space imperative, a compelling reason to venture into space, is to gain a global perspective. In other words, we're simply trying to get higher so we can see more of the Earth. Space is the ultimate high ground. If you've ever traveled around Europe and toured medieval castles, you've noticed where they built those castles. Not in the valleys, on the hills. They wanted to be able to see the bad guys coming from afar away. Today we put observation platforms in space for exactly the same reason, to see more. In this respect, there's nothing special about being in space or in orbit. In fact, as we'll see, the vacuum, radiation, and other hazards are an annoyance, but we put up with them in order to see more of the Earth from a given vantage point. This satellite toolkit animation illustrates how useful that global perspective can be. Here we see a single satellite in low Earth orbit, only about 700 kilometers above the surface. Yet a camera on this one satellite can cover vast areas of the Earth each time it circles the globe. We'll examine exactly how much you can see from a given orbit, and how well later in the course. Another important motivation to go into space is to gain a clear view of the heavens. If you've ever looked up at the stars on a clear night, you've seen the familiar twinkle. While Twinkle Twinkle Little Star makes a nice nursery rhyme, it's an annoyance to earthbound astronomers who must peer through the atmosphere at their objects of interest. That familiar twinkle is an effect known as scintillation, but scintillation, little star just never caught on. Scintillation is the diffraction of starlight as it passes through the atmosphere. This diffraction bends the light and absorbs some of it and distorts it, making it much harder to get a clear picture. But by putting telescopes into space, we can get above the atmosphere to see more with the same size telescope. The Hubble Space Telescope shown here is able to take such amazing pictures of the universe because it is unhampered by the atmosphere. As we'll learn later in the course, satellites, or humans in orbit, are not in zero gravity. Rather, they are in a condition better described as free fall. They're constantly falling. While astronaut Susan Helms, shown in this video, is having fun running around the International Space Station, this freefall environment also offers another unique advantage of space that can't be duplicated here on Earth for more than a few seconds. As we'll see, the freefall environment can enable manufacture of new materials and other processes of potential great benefit to science and society. Space is boundless, and so are the potential for resources, which is another compelling reason to go into space. Satellites and the International Space Station already take advantage of the boundless solar energy available in space. One day, astronauts may use other resources on the Moon, asteroids, or Mars to live off the land. The last space imperative we'll present is the most compelling for scientists, or anyone who's ever gazed up at the night sky and wondered about the universe and man's place in it. Space demands our attention as curious humans. We go to space because it's there, because it truly is the final frontier. Russian space pioneer Konstantin Tsiolkovsky once said, "The Earth is the cradle of mankind, but we can't stay in the cradle forever." Through space exploration, we learn more about the nature of the cosmos, other planets, and Earth itself. The Mars exploration rovers, shown here, have served as tireless prospectors, investigating the Martian surface to help us rewrite our understanding of Earth's closest cousin in the solar system. Now that we've examined the space imperatives, those 5 compelling reasons to go into space, let's turn our attention to space missions. Let's describe the types of space missions common today and how each takes advantage of the space imperatives. We'll start with the first space imperative, global perspective, and look at 3 of the most important space missions flying today: communications, remote sensing, and navigation, that use this perspective to provide vital services to civil, military, and commercial users all over the planet. The idea of using high ground to relay messages between distant points is not new. For centuries, people have used flags, mirrors, and smoke signals on hilltops to communicate with others in the valleys or beyond. But in 1945, science fiction writer Arthur C. Clarke proposed taking this idea to the extreme by putting a relay station in a special type of orbit called geostationary. That station could appear to be motionless above a given spot on the equator, allowing users who otherwise could not communicate over the horizon, but who can both see the relay station high above, to send messages back and forth. It is the single most important application of space there is, and where most of the money spent on space projects goes. Today there are more than 300 satellites in geostationary orbit that link together our global village, allowing almost anyone, almost anywhere, to talk to almost anyone else. Without this capability, U.S. military global reach would not be possible. This graphic, not to scale, shows the relative location of these satellites. From this perspective, you might get the impression that space is crowded. But again, this is not to scale. As we'll see, space is big, really big. But even so, there are crowding issues, especially in this popular orbit, but primarily from the standpoint of satellites potentially crowding each other out in terms of frequencies. Just like you don't want 2 radio stations next to each other on Earth at the same frequency, a great worldwide effort is made to deconflict frequencies at geostationary orbit as well. We'll also see later in the course that space debris at geo is becoming a bigger issue. A special application of communications, but one that is so important it deserves its own category, is navigation. Ancient mariners used lighthouses in known locations to tell them where they were at sea. The United States Air Force Global Positioning System, or GPS, provides far more precise navigation information to any user on the planet. By placing a number of identical satellites in similar but different orbits, we create a constellation that together makes it possible to receive a communication signal from 4 or more satellites simultaneous anywhere on the globe. With this information, users with an inexpensive GPS receiver can determine their position, where they are, their navigation, where they are going and how fast, and most important, the time. With their precisely tuned atomic clocks, GPS has become the universal timing reference for the entire Earth, used for cell phones, ATMs, and numerous other applications. GPS has become so important to the world economy that the European Union is developing their own complementary system called Galileo. The Russians already have a similar system called GLONASS. Another critically important mission, especially for national security, that capitalizes on the unique global perspective space offers is called remote sensing. Remote sensing is a broad term that includes any type of mission that monitors some aspect of the Earth or another planet if I'm orbiting around it. This could be a broad focus, such as all of North America for weather forecasting, or very tightly focused, counting cars in a parking lot. This capability was originally developed by the U.S. Air Force, in parallel with their Soviet counterparts during the early days of the Cold War, to monitor strategic capabilities, missiles, tanks, ships, and the like. However, since those early days of exclusively military application, remote sensing has grown to be vitally important for environmental monitoring, weather prediction, agricultural planning, as well as disaster relief. The image shown here were taken from Digital Globe's WorldView 2 satellite and shows before and after pictures of the recent earthquake in Haiti. Such detail and timely information is incredibly valuable to organizations mounting rescue and recovery relief operations. Now that we've looked at the missions that leverage global perspective, let's see how a different set of missions use that second space imperative, that of providing a clear view of the heavens. We'll examine two types of missions here, space astronomy and solar observatories. Earlier I mentioned the Hubble telescope as an example of a satellite that does its job so well because it is above the obscuring twinkle of the Earth's atmosphere. But Hubble is only one of dozens of telescopes that have peered to the ends of the universe. From X-ray to infrared and radio frequencies, these cosmic sentinels have transformed our understanding of the universe, helping to define its age, evolution, structure, and ultimate fate. The European Space Agency's Planck satellite is mapping the cosmic background radiation, giving us hints as to how galaxies were formed. NASA's Swift telescope keeps its wide eyes peeled to detect powerful but short-lived gamma-ray bursts, then training its detailed telescope on the event while cueing Earth-based instruments to do the same. While space astronomy studies stars at the edge of the universe, another class of missions monitor a star much closer to home, the Sun. SOHO, STEREO, and most recently, the Solar Dynamic Observatory, SDO, study the dynamic nature of our closest star to understand its long-term behavior and alert us in the event of potentially lethal solar flares. This movie shows some of the first images collected by SDO, showing the tumultuous nature of that life-giving ball of fusing hydrogen at the heart of our solar system. Finally, let's turn our attention to missions that take advantage of the freefall environment, the potential for abundant resources, and that plumb the depths of the final frontier. As you sit there at your desk, gravity is pinning you to your chair. In the coffee cup beside you, gravity is slowly pulling undissolved sugar and other particulates to the bottom of the cup. Now imagine the floor in your desk disappeared. You started accelerating toward the center of the Earth at 9.81 meters per second squared. While you probably have other things on your mind as you fell, in your coffee cup the sugar and particulates are now falling at the same rate as the liquid, so they stay mixed. In a 1G environment on the Earth's surface, some chemical reactions are impeded. The growth of crystals is a good example, shown here. Zeolite is a crystal that readily absorbs hydrogen. It is of keen interest to engineers studying the possibility of hydrogen-powered cars. But as the photos illustrate, crystals grown on Earth can't grow very large. But zeolite crystals grown in space in the freefall environment grow many times larger, offering the potential to store hydrogen for propulsion and other power applications. While still in the experimental stage, zeolite, along with dozens of other possible applications for freefall manufacturing, are currently being investigated. With energy and water, life as we know it become possible. Using resources beyond Earth to fuel the expansion of humans into the solar system has been the stuff of science fiction for decades. Satellites already take advantage of the abundant sunshine in space to make energy. But the Apollo missions and more recently the L-Cross mission to bombard the lunar pole have demonstrated that the moon offers a vast array of raw materials, from the lunar soil, from which oxygen can be extracted to breathe or use as rocket propellant, to water ice in the dark crevices of the poles. Similarly, Mars and the asteroids also hold vast amounts of water. The resources to live off the land are there for the taking, but getting there and exploiting them remain a formidable technical challenge. The idea of boldly going where no one has gone before excites anyone with a natural curiosity of the universe and our place in it. Did life begin on Mars billions of years ago in parallel with Earth, only to be snuffed out as it lost its atmosphere? Is there currently life teeming in the oceans below the frozen surface of Europa? Or are there exotic forms of life that live in the hydrocarbon lakes of Titan? Robotic explorers like Voyager 1 and 2 have visited the distant planets of our solar system and are now leaving it to be the first human-made objects to venture toward the stars. The Mars Odyssey spacecraft and its sisters in Martian orbit, the Mars Reconnaissance Orbiter and the European Mars Express, circle the red planet a dozen times a day, peeling back its secrets. The Cassini spacecraft traveled to distant Saturn to study that ring planet and drop the Huygens probe to land on the surface of Titan. Numerous other spacecraft around the solar system continue to fuel our curiosity, sometimes posing more questions than they answer as we learn what a wondrous neighborhood we live in. While robots can dutifully supply data, they don't provide a human face to the exploration of space. Since Yuri Gagarin became the first of our kind to venture beyond the atmosphere, astronauts and human exploration has served as a source of inspiration for us all. Today there is a continuous human presence in space aboard the ISS. Future missions beyond Earth orbit are eyeing the asteroids as a stepping stone to Mars and other destinations. In this lesson, we started out by asking, why space? What is it about space that compels us to go there? Answering that question, we examined the space imperatives, especially the boon of a global perspective, but also a clear view of the heavens, a free-fall environment, the promise of abundant resources, and the beckoning of the final frontier. We then explored the types of space missions we commonly find today. starting with those that exploit that global perspective: communications, remote sensing, and navigation. Next, we saw how space and solar observatories above the atmosphere are shaping our understanding of distant stars as well as our local star. Finally, we looked at how robotic and human missions are pushing our knowledge and presence beyond the cradle of mankind. This concludes the Space in Our Lives lesson. Be sure to check out the recommended reading for further background. Thank you for your time and attention, and see you next lesson.